So this is Lecture 2C, welcome. And title is Non-Existence of a Limit. In Lecture 2B, we looked at examples where we could apply techniques to check if the limit exists. In this case, we're going to apply techniques which we can use to determine if the limit does not exist. There's some guesswork involved because you have to assume one or the other, determine which approach to take. Clearly, if you fail at one, it's probably the other. So again, this material is from chapter 15.2 of the text. And the objectives here are determining the non-existence of limit for a multivariable function and illustrate the method used to determine if the limit does not exist for two variable problems. And so we're going to be focusing on the two-path test, which is basically a contrapositive proof. All right, so as usual, the second slide basically is just a summary of the slides to follow. And so there's 6 items that are going to be covered. All right, so next would be, what is the process to follow if you assume that the limit does not exist? And so we have 2 bullet points here. The first thing we would do is to simplify the final functional expression so that the resultant expression consists of polynomials or well-known functions for which it is possible to show that limit does not exist using the two-path test. The other is the two-path test, which is to prove that for at least 2 different paths approaching the boundary point, which means we're dealing with an open set, you get a different limit. So this is basically the process we follow. All right, so let's consider the change of variable options to implement a two-path test. And we're looking at 2 specific cases that we'll look at in this course. There are, of course, others as well. One of them in which we basically change both x and y and make them function of 2 new variables, u and v. And another option is to essentially make y a function of x, but to some exponent x with some sort of constant m. And this m value basically represents different path. So if you choose m equals 1, that would represent one path. If you chose m equals 2, it would represent another path, and so on. The choice of n in the exponent here would be made by the user. And the idea would be to choose n in such a way that the one of the functions, in this case x, on the numerator and denominator will cancel out, and you end up with only a function of m. That's basically the objective, is to choose n in such a way that you get that desired result. Or you could do a substitution involving x as a function of y to a power n times m. Anyway, these are things which basically are up to the user to decide, and of course will differ depending on the nature of the problem. All right, so the objective is to choose functions for approach 1 or a function for approach 2 that lead to an expression that allows you to find at least 2 paths for which the limits are different, u or v for approach 1 and m for approach 2. All right, so for approach 1, basically, we're essentially saying that if we end up with an expression in which the final results involve just a function of u or function of v, then the limit will depend on just the new variable. And so there'll be a mapping between the old boundary point and the new boundary point. The most common two-variable transformation, if you see an expression that involves x squared plus y squared, and the boundary point is at 0, 0, is the following expression shown here. And so if you wanted to map every point x and y to every point in the uv domain, then v would be greater than or equal to 0, and u would range between 0 and 2 pi. So this is typically an expression we would use. Mind you, this is only if the boundary is at 0, 0. This would have to be modified if that's not the case. And again, just to reiterate, it's a mapping from the uv plane to the xy plane, and it's 1-to-1 and onto. And approach 2 basically is to make the substitution either for y, mx to power n, or for x, m, y to power n, such that the resultant after simplification is only a function of m, and m basically represents different paths, and therefore because it depends on variable m, the limit does not exist. These are again our substitutions applicable if the boundary point is at 0, 0. Okay, so let's go through an example for approach 1, the change of variable example. Objectives to determine if the following limit exists. Z is the limit of as xy approaches 0, 0 of x plus y squared over x squared plus y squared. And judging by the function, it's clear that the denominator can't be 0, which occurs when x equals y equals 0. Hence, it's a boundary point for the domain. So again, we see here the x squared plus y squared, so which suggests that we use the substitution x equals v cos u and y equals v sine u. And again, as mentioned on the previous slide, v will be greater than or equal to 0, and u will range between 0 and 2 pi. As far as a mapping is concerned, you see the picture on the right. So if we're talking about v would be the distance along a radial line. So you change v, you lengthen this line. And u is taken to be an angle, either in radians or in degrees, which is in a counterclockwise direction. And so, for instance, this would be an example of 45 degrees or pi over 4. And this only can sweep once around. That's from 0 to 2 pi to do essentially a 1-to-1 and onto mapping. All right, so the boundary point here is 0, 0. That's when we choose x and y, but we have to map this now to the UV plane. So this only occurs if basically VU is equal to 0 and u. That's the under condition under which you can basically achieve the same result. So the 0, 0 would be the origin. All right, and so as we mentioned, the u value can take any value between 0 and 2 pi. So we take this expression, substitute for x, substitute for y, and we end up with this expression here with v approaching 0. If you simplify this, you'll have a v squared, which is common to numerator and denominator. That cancels out, and you're just left with this expression here. Well, this limit will depend on the value of u, which means this angle here, which means depending on whether or not you go in this direction or this direction, the limit will be different. And therefore, because the limit changes as a function of u, means that the limit does not exist. All right, so let's look at the same function, but using approach 2. So here, basically, the easiest thing to do is to check the order of the numerator and the denominator. You'll notice here there's a square and a square. They're equal. And here, you're going to end up with x squareds and y squareds and xy, so also equal. So the simplest thing would be to just choose y to be equal to mx, where m will represent the slope of the line. You change the value of m, and then you'll change the value of the slope of the line in the xy plane. So we just make the substitution for y, which is here. And then after some simplification, we end up with 1 plus m squared divided by 1 plus m squared. Clearly, if you choose different values of m, the limit will be different, and therefore the limit does not exist. All right, so if we're to draw this on a diagram, which is what you see down here, you can see that for m equals 1, you have a line, right, in the first quadrant. For m equals 0, it's along the x-axis. M equals minus 1, basically, it would be in the second quadrant and the fourth quadrant. And so these are just different paths, all basically finally ending up at the point 0, 0. If we were to graph this particular curve, then this function, this is what we would see. And you can see this is the level curve for z equals 2. And this is the level curve for z equals 0. Okay. So it's clear that the limits will differ depending on the path that was chosen. So here's an interactive module where you can choose different values of m, basically different paths, which then take you to the point. Here, basically, this would be an example for this, m equals 1, substitute in here, and you'll end up with a value 2. You can choose any values from m equals minus 2 to 2, just to show what the result will be. All right, so let's look at another example. This is change of variable example 2. Using approach 2. In approach 2, we essentially said that we could let y be some function of x to a power of n times some constant, or the other way around, x is some function of y to a power of n times a constant. In this case, the function is shown, and we'll notice that the x and y approaches 0, 0. If you plug in the values of 0 in the denominator, it's clear that the denominator is 0. That means the function is undefined, and hence the 0, 0 point is a boundary point for the domain. So that's something we need to make sure of right at the outset. So Here's where a matter of experience comes into play in terms of how do we select the relationship between y and x. In this case, we're looking at the numerator and the denominator. They all involve powers of 2 in terms of exponent. And so we're going to choose y equals mx. And we make the substitution. And you'll see that you'll get an x to 4th term in the numerator. And you end up basically with an x 4th term and an x squared term in the denominator. Now you might say, well, they're different. Well, in this case, it's a very special type of function. And as we'll see here, in fact, we can determine the limits. And so we don't have to worry about the fact that we have 2 different variables, but it's a special case. So if we look here, after simplification, what we do is we divide through by x to the power 4th, which means that we only end up with a term x to the minus 2 here. And so we look now at 2 scenarios. We look at the scenario where m equals 1. And why do we do that? Because of the special nature here, that if m equals 1, this term becomes 0. And the case where m is not equal to 1. Well, if m is not equal to 1, then these are just numbers. And so as x goes to 0, x to the power minus 2 goes to infinity. But a number over a very large number, basically, and the limit is 0. So you end up with a value of 0. The other case is where we set m equals to 1. In that case, this term becomes 0. We have m squared over m squared, which is 1. So in this case, the limit is 1. Well, we know this by the 2-path test, that if the limits are different, then essentially the limit does not exist. Just a general note, if you find that the limit along all lines is equal, you cannot conclude that the limit exists. Instead, you should try along other curves if you suspect the limit doesn't exist. This is where the skill and experience play a role. Here we just chose 2 tests, and that was enough to convince us that the limit did not exist. Okay, so the last example 3 is this one involving absolute value, which is bit of a tricky function, but there's a simple way to deal with it. So we want to look at the limit as xy approaches 0 for absolute value xy divided by xy. Clearly, the point 0, 0 is a boundary point for the domain. Now, a little trick that you can employ is basically to take the absolute value and represent it in form of an analytical function. So if you take the square root of xy squared, and take the square root, you end up with xy. However, the square root can only be positive. So in fact, the square root of xy squared is equivalent to the absolute value of xy. It's a very simple trick, and so you'll find this is a very easy way to work with anything involving absolute values. So you'll notice that the order of the numerator and denominator are more or less the same, or they are the same. So let's choose y equals mx in this case. So if we choose y equals mx and simplify, we find that we end up basically with this expression here. The square root of x to the 4th is x squared. It's always going to be positive. The x squareds cancel. But the square root of m squared is the absolute value of m. So this becomes absolute value m over m. That is the limit as xy approaches 0, 0. So consider the paths for m equals 1 and m equals minus 1. So the limit in the former case is 1. The latter case is minus 1. Therefore, the limits are different and means that the limit does not exist. So that concludes lecture 2C. Thank you very much for listening to the lecture.